Hi everyone, welcome back to my video on control systems. In this video, I'm going to show how do we sketch the Bode plot of the system by combining a few subcomponents that we derive from the systems. Before going further, I hope that you have already viewed my video on the sketch of the subcomponents derived from the Bode plot. Okay, let's look at this transfer function, s plus 10 over s plus 5. For this transfer function, it is expressed in terms of the Laplace variable s, which we are not going to use it in our case here. We have to transform this into our standard form. Let's do this, and it will result us into gj omega equals to 2j omega over 10 plus 1 divided by j omega over 5 plus 1. You will see an additional 2 here simply because it is a result after conversion into the standards form for the ease of the Bode plot sketching. We can observe here there are actually 4 elements. First one is the 2, which is our simple gain, followed by our first order 0 with a natural frequencies, or what we say usually will be the corner frequencies of 10. And also we have one pure integrator j omega, followed by our last term, which is the first order pole with the corner frequency of 5. And you can see here that I also listed the 2 expressions describing the magnitude and the phase value of the system. Let's begin with plotting the Bode plot of a simple gain of 2. When we find the decibel equivalent of 2, we use 20 log base 10 of 2, which will give us roughly about 6 dB. So let's use the approximated value 6 dB in our sketching. For the magnitude plot, it will be just one straight line from the start until the end at the magnitude of 6 dB. As for the phase diagram here, basically we are going to see that is a 0 for the entire frequency for the simple gain. Next, we move to the first order 0 with a corner frequency at 10. For the magnitude plot, you observe always 0 from the start until the corner frequency 10. So after 10, it will rise at a slope of positive 20 dB per decade. So what we need to do here is that we will locate one point at 0 at a frequency of 10. And next we locate another point which is at 1 decade afterward, which is 100 radian per second. And we put up a 20 dB over there. So by connecting these 2 points, we can have one straight line of 20 dB per decade. For the phase, it will start at 0 and you continue at 0 until it reaches the frequency where it is 1/10 of the corner frequency. Then it will rise up and it will reach 45 degree at the corner frequency. So after that, it will rise to 90 degree when it's reached the 10 times of the corner frequency, which is 100, and it will stay there forever until the end of the plot. That will be our phase diagram for the first order 0 with corner frequencies of 10. Next, we move to the integrator. The magnitude plot of the pure integrator will be a constant slope of negative 20 dB per decade, and it will cross at 0 dB at a frequencies of 1. So basically it will be something like this. And next we will move to the phase diagram, and a phase diagram of a pure integrator will be always at negative 90 degree regardless of what values of the frequency. Okay, so we are done with the integrator. Our last term will be the first order pole with a corner frequencies of 5. For the magnitude plot, basically it is one straight line with 0 dB until it reaches the corner frequencies of 5. And then it will continue with a downslope of negative 20 dB per decade, starting at corner frequencies 5, and then it will go on forever. So basically to sketch this, we just need to locate 2 points. One it is 0 dB at corner frequencies of 5, and the next point will be negative 20 dB at the frequencies of 50, 1 decade afterwards. As for the phase plot, basically the idea will be pretty much the same as the first order 0, except that all the lines are now flipped downwards. So in this case here, you will be observing one straight line at 0 degree from the start until the frequency of 0.5, which is 1/10 of the corner frequency 5, and you'll be negative 45 at the frequency of 5, and you'll be at the negative 90 at 10 times of the corner frequency, which is 50. Afterwards, you will stay at negative 90 degree. Okay, these sketches over here will describe the individual subplot of the Bode plot, but we still need to have one complete plot that describes the Bode plot of the entire system. So what we need to do is just to graphically sum all the points together. So let's look at the magnitude plot. Okay, we can take one reference point where the frequencies is equals to 1, and at the frequency equals to 1, the magnitude will be 6 dB. Anything before that, it will be one slope of 20 dB per decade. And then this slope will carry on, okay, until we meet the first corner frequency, which is equals to 5. At this point, the slope will become double of it because of the contribution from the first order pole as well as the pure integrator. But the slope will be slightly lesser when it reaches the next corner frequency, which is equals to 10. The slopes will be reduced to negative 20 dB per decade, and it will carry on for the rest of all the frequencies until infinity. Okay, so we left the last part, which is the combined phase plot. As you can see from here, the phase plot will be always starting at negative 90 degree. It will be carry on for all the frequencies until it reaches the first corner frequencies divided by 10. In this case here, it will be 0.5. At 0.5, you start to go down, and you will slowly be balanced off by the next point that you see here, which is 10 times lesser than the next corner frequency, which is equals to 1. After 1, you won't be able to see that the slope is going down furthermore because it will be balanced by the line above. In this case here, you will just have a small slope, small little downhill over here, then going up back, and then you keep steady at negative 90. Okay, and you carry on to stay at negative 90 for the rest of the frequencies. Okay, this will be the complete Bode plot that combines all the individual components into one. Let's compare with the Bode plot generated using Matlab. So using Matlab, we can generate the Bode plot using two commands. One is using the Bode command, Bode, followed by the transfer function G. And the other method will be to use the function called margin. Basically, these two commands will return with the same sketch, but margin will give you additional information on the stability margin. And you can see that basically the plots that is obtained from the Matlab is quite similar to the one that we actually sketch in here. Even though we do not have a very good sketch, however, it is still good enough for us to do our basic analysis on it. Okay, that's all for this video. Thank you very much for watching. Bye.